Have you ever stopped to wonder how your computer actually keeps secrets? Well, it turns out the answer has its roots in something you probably learned back in high school algebra: polynomials. Today, we're going to uncover the surprisingly elegant link between these simple equations and the super complex cryptography that protects our entire digital lives. So let's just dive right in with this question. What on earth does an expression like x squared plus 1 have to do with computer security? I mean, it looks like a homework problem, right? But believe it or not, this is the key. This simple little polynomial represents a brilliant trick for taking the raw language of computers, all those ones and zeros, and turning it into a mathematical object we can actually work with. It's the foundation for pretty much everything we're going to talk about. All right, so here's our roadmap. First, we'll see how to turn simple bits into polynomials. Then we'll do a quick math refresher before we add a really cool cryptographic twist. After that, we'll look at the specific way computers do this math, find some special prime polynomials, and then we'll see how it all comes together to form the bedrock of modern security.
Okay, first up, let's get from bits to polynomials. So here's the basic challenge, right? Computers speak in bits, ones and zeros. Mathematicians, on the other hand, have spent centuries developing these incredibly powerful tools for handling polynomials. The first big step is just building a bridge between those two worlds.
And this is the trick. Right here. It's so clever. We can map any pattern of bits directly to a polynomial. Just think of each position as a power of x. So if you have the bit pattern 1, 0, 1, the rightmost one is the constant. The 0 in the middle means we have 0 x's, so that term just vanishes. And the 1 on the left is in the x squared position. Put it together and you get x squared plus 1. Simple, elegant, and incredibly powerful. And this works for any string of bits, not just short ones. This general formula shows how it works. Those a coefficients you see, they're just our ones and zeros. This translation is a complete game changer. It means we can take any piece of data on a computer and start applying all the rules and power of algebra directly to it. So, before we get to the really cool cryptographic magic, let's just take a second and dust off those old algebra skills. We need to remember the basic rules for polynomial arithmetic. Yeah, this stuff probably looks pretty familiar. When you add or subtract, you just combine the terms with the same power of x. For multiplication, you use methods like FOIL, and for division, you do polynomial long division. This is all standard textbook stuff, but it's about to get a very, very interesting twist. And here we go. This is where we leave normal math behind and really enter the world of cryptography. Instead of letting our numbers be anything they want, we're going to force them to live in a very small, very specific set of numbers. This is what's called working in a finite field. Let's use the finite field GF7 as an example to see how this works. In this world, the only numbers that exist are 0 through 6. That's it. Anytime you do some math and the answer is 7 or bigger, you have to wrap it back around. It's just like a clock. On a 7-hour clock, if it's 6 o'clock and you add 2 hours, it's not 8 o'clock, it's 1 o'clock. You just divide by 7 and take the remainder. Now, this is where the math gets a little weird, but also really powerful. Let's look at this division. The first step is to divide 5 by 2. Now, normally that's 2.5, but we don't have decimals here. Instead, we have to ask ourselves, what number in my world of 0 to 6 can I multiply by 2 to get 5? Well, let's see. 2 times 6 is 12. And 12 on our 7-hour clock, well, that's 5. So in G of 7, 5 divided by 2 is 6. It's strange, I know, but if you apply that same logic at every single step, you can still do complex division. It just works. Okay, so GF7 is a cool example to wrap your head around the concept, but it's not what computers use. Computers don't count in 7s, they count in 2s. So let's get to the main event, the most important finite field for all of computing, Galois field 2, or GF2. The world of GF2 is as simple as it gets. The only numbers are 0, 1. That's it. And the math rules are almost what you'd expect, but with one crucial exception. Look at the addition table. 1 plus 1 equals 0. Why? Well, it's the same modular arithmetic as before. 1 plus 1 is 2, and 2 divided by 2 leaves a remainder of 0. This one little detail is everything. And here's the absolute magic of it. This abstract math we've just defined maps perfectly onto the physical hardware of a computer chip. Addition in GF2 is exactly the same thing as the logical XOR operation, and multiplication is the same as the logical AND operation. This is huge. It means we can perform all this advanced polynomial math using the absolute fastest, most fundamental operations a computer processor can do. It's incredibly efficient.
All right, so we have our building blocks. We've got polynomials whose coefficients are just ones and zeros, and we have the rules of GF2 to do math with them. We're almost ready to build something secure. We just need one final piece of the puzzle, a special kind of polynomial that behaves just like a prime number.
This special piece is called an irreducible polynomial, and the idea is really straightforward. You know how a prime number, like 7, can't be factored into smaller integers? Well, an irreducible polynomial is one that can't be factored into smaller polynomials. They are the fundamental, unbreakable atoms of this system. I really want this analogy to sink in because it's so important. Just like prime numbers are the basic building blocks for all other integers, these irreducible polynomials are the basic building blocks for creating secure cryptographic structures. They give us a boundary, a modulus, that we can't break down any further, which is absolutely critical for security. All right, let's put it all together now. We've got bit patterns as polynomials, we have our finite field GF2, and we have our unbreakable prime polynomials. Let's see what kind of powerful structure we can build with these pieces.
So let's just do a quick recap. We figured out how to turn bit patterns into polynomials. Check. We learned how to do math with them in the supercomputer-friendly world of GF2, using just XOR and AND. Check. We found our irreducible polynomials to act like primes. Check. When you combine all of that, you create this consistent, powerful mathematical system called a commutative ring. Now, that sounds fancy, but all it really means is we've created a special universe where our math always works exactly as we expect it to.
So why does this all matter? I mean, what's the big deal? It matters because this carefully constructed mathematical engine isn't just a curiosity. It is the real-world engine that powers things like AES, the Advanced Encryption Standard. This is the math protecting your bank transactions, your private messages, government secrets, you name it. It's the foundation of our digital security, and it's chosen because it is incredibly fast and provably secure. So we've built this amazing structure, this ring of polynomials. But for the kind of ironclad, maximum security used in systems like AES, cryptographers need something even stronger. They need to turn this ring into a true, unshakable, finite field. And so the big question we're left with is, how do we do that? How do we take these building blocks and forge them into the cryptographic standard that protects us every single day? Well, that's the next step in the story.